Okay, so in this section we're going to be discussing vectors in a plane, and we're going to go through 6 examples, probably separated into 2 different parts. Here's your homework. Let's go ahead and get started. A vector is a directed line segment, and here we have a directed line segment. We have an initial point and a terminal point, and that vector is written as v equals PQ. We have a little line over it showing that it is a directed line segment. A vector is defined in terms of its magnitude and its direction. The magnitude is literally the length, and the direction is the slope or the angle that is made with the x-axis. So magnitude is represented with lines that surround the vector. Some books have 2 lines on either side. Our book simply just has 1 line on either side. So vectors can have different positions yet be equal to each other. For instance, vector v equal w because they have the same length and they have the same direction. So we have v and w here have the same length but different directions. They're not equal. These 2 vectors have the same length but different directions. These ones here have the same directions but different lengths. So we show that 2 vectors are equal to each other by proving that the magnitudes are equal and the directions are equal. So if we want to find out the magnitude of the vector, then we literally need to figure out what the length of the vector is, which is essentially the distance formula. So subtract the 2 x values and subtract the 2 y values, and you're going to have the legs of your triangle here. So we have a 3 here and we have a 6 here, and we can find out the length of vector v by using that distance formula. Essentially, it's the Pythagorean theorem. So we have 3 squared plus 6 squared. Take the square root of it, and we end up with square root of 45. So in order to figure out the magnitude of the other, we do the same exact thing. We want to figure out that length there, and so I'm just going to make a right triangle, and distance from here to here, that's a 3, that's a 6. So once again, we're going to end up with a magnitude of 45. So we know the lengths are the same. Now we need to figure out, are the directions the same? Well, the directions we can find by looking at the slope. The difference in y over the difference in x tells us the slope, and they both have a slope of 2. So we can say yes, they are both equal to each other. These 2 vectors are equal. So a vector is written with component form, and if v is a vector in the plane equal to the vector with initial point at 0, 0 and terminal point at v sub 1, v sub 2, then the component form of v is equal to this right here. So let's say we have the initial point here, terminal point somewhere out here. We'll call that v sub 1, v sub 2. And this here is our vector written with the component form like so. We're going to get a little bit of practice with a couple of examples here. Let's start off with this one here. We have vector v equal 3, 4. So to find out what that vector looks like, we go out a distance of 3, go up a distance of 4, and we got vector v right there. One thing to take note of is that the vector v here is going off in the positive x and positive y direction, and we have positive components here. Let's look at the next one here, part B. We have negative 2, 3, and we go out a distance of 2, up a distance 3, find the next vector. And that vector has, it's going off in the negative x direction, the positive y direction, and that's represented in the components there. Let's just look at one more, part C. We go out, -3, we go down, -4, and so we have our vector going off in the negative x and the negative y direction, and that's represented once again in our component form. Okay, let's move on to the next one. Well, you can have a vector that doesn't have the initial point at 0, 0. So let's say we have vector v represented by a directed line segment PQ with the initial point other than the 0, 0 and terminal point Q. Then you find the component simply by subtracting the two x values and subtracting the two y values. So let's say we have initial point P here, terminal point Q here. Here's our directed line segment. If we want to find the component form, then we simply take a difference in our x values and take a difference in our y values, and that will give us our component form of our vector. So let's get an example here. Let's say we have point P. We're finding the component form of PQ, and we have point P at -3, 4, which is right here, and we have Q at -5, 2. So -5, 2 is right here. Now there's our vector. We want to find out what the component form is equal to. So literally we just need to subtract our x values and subtract our y values. One thing I forgot to mention here might help you guys to think terminal minus initial to find the component form. So I'm going to take my terminal first, which is with point Q, so -5 and then -3, -3, and then we take terminal, so 2 minus 4, and we end up with component form at, we have a -2, -2 for our component form. Now, you could represent that vector also right over here with initial point at 0, 0. These two vectors are equal to each other because they have the same direction and the same magnitude. Okay, let's move on to the next one. The magnitude of the vector is once again essentially just the distance formula or the Pythagorean theorem. So let's move on to an example here. We want to find the magnitude of the vector that we just looked at. So I'm going to jump back over here. If I want to find the magnitude of this particular vector, essentially what we're doing here is we're looking at the vector as the hypotenuse of a right triangle. And so if we have one leg here, which is a 2, and another leg here, which is a 2, we can find out that distance, the magnitude of V, by using the Pythagorean theorem, or the distance formula. So we have 2 power 2 plus 2 power 2, and that gives us an 8. Square root of 8 is 2 root 2, because 8 is 4 times 2. Take the square root of 4, that's 2. Alright, jamming along here. Let's move to vector addition. We add two vectors together simply by taking the taking the components and adding them up. So take the first component, add to the first component, second component added to the second component. We're going to look at this geometrically, and then we're going to look at an example as well. So let's say we have vector u, and we're going to add that to vector v. In order to add them up and look at the geometric representation, we want to position u and v so that the terminal point of u coincides with the initial point of v, right here. And the resultant vector of u plus v extends from the initial point of u all the way to the terminal point of v. So that is the geometric representation. Now, a lot of times, like in physics, you guys will see the force of one and the force of another and combine those two forces into one, which is right here, u plus v. Let's look at an example here. And here I have, oops. Some vectors drawn. I'll pull these out of the way. So we let u equal this, let v equal this. We want to find the component form of these vectors added up. Well, it's pretty darn easy to simply just add them up. You just need to add -1 to 4, -1 plus 4, and then 3 to 7. And that gives us, we have 3, 10. So let's go ahead and see what this is geometrically speaking. We're going to get a good visual of what's going on here. So let's say we have, let's look at -1, 3. So we go -1, 3 is the vector going from here out to here. That's our u. And we also have another vector at 4, 7. So 1, 2, 3, 4, and then 7. Okay, so we got vector v right there. Now we want to know what u plus v looks like, and we can look at that by taking the initial point of u, the initial point of v, and connecting it to the terminal point of u. The resultant vector is going to go from the initial, what was that? From the initial point of u to the terminal point of v. This is, in purple, this is represented by this component form here, 310. And one thing I'm noticing here is that I have a +3 and a +10. And this vector here in purple is going in the positive x and the positive y direction. Okay, so another thing is that I moved this vector from here to here, which is okay because I didn't change the magnitude or the direction. It's still an equal vector. I just changed the position within the xy system. Alright, scalar multiplication. Scalar multiplication is when we multiply a vector times some value. See, we have vector v here. If you multiply times a 2, then it extends. You know what I'm going to do? I'm going to just cut off right here and pick up right at scalar multiplication.